story of the B-2 Spirit begins not in the air, but in the minds of strategists confronting a new reality. By the 1970s, surface-to-air missiles, early warning radars, and integrated air defenses had begun to render conventional bombers increasingly vulnerable. Speed alone, once the defining feature of strategic bombers, was no longer enough. Flying faster might let you outrun some threats, but it could not hide you from a world that was watching, tracking, and preparing to strike the moment you appeared on a radar screen. The B-2 Spirit was designed to confront that reality head-on. Its design philosophy was revolutionary. Survive in contested airspace long enough to complete the mission. Every curve of its wings, every edge of its fuselage, every intake and exhaust was engineered with a single, relentless goal: to avoid detection. Unlike traditional aircraft, the B-2 did not rely on outrunning the enemy or on overwhelming firepower. Its power lay in invisibility, in the ability to slip through the most sophisticated defenses and strike with certainty. At first glance, the B-2 seems alien, almost sculptural. Its flying wing configuration defies conventional expectations of what an aircraft should look like. There are no vertical tails, no protruding engines, no obvious appendages. This is not aesthetics for its own sake. Every design choice reduces the aircraft's radar signature. By blending shape and surface, by carefully managing angles and reflections, the B-2 achieves a stealth profile that confounds even advanced detection systems. Inside, the B-2 is just as extraordinary. Unlike earlier bombers, it is not a simple payload carrier with engines attached. It is a complex ecosystem of sensors, avionics, and mission systems, all integrated into the airframe. Fuel, weapons, and electronics are meticulously packaged to preserve stealth while maximizing operational range and payload flexibility. Internal bomb bays allow the B-2 to carry its arsenal without compromising invisibility, a capability that would have been impossible on earlier aircraft without massive drag and radar exposure. The engines themselves are hidden within the wings, with exhausts carefully managed to reduce infrared signatures. Even the materials used in construction are optimized to absorb radar waves, turning what would be a reflective surface into a near-transparent one for enemy sensors. Every maintenance check, every flight operation, every mission plan is oriented around the same principle: minimize risk, maximize surprise. But stealth alone does not make a bomber effective. The B-2 was designed with range and payload in mind, capable of flying from bases in the United States to targets on the other side of the globe. It is fueled for endurance, able to penetrate deep into hostile territory and return safely. This is not just engineering, it is strategic thinking. The B-2 allows planners to reach targets that would have been impossible for older bombers, striking with precision while avoiding catastrophic losses. The operational philosophy of the B-2 represents a dramatic shift from the past. Bombers were once judged by speed and payload. They were expected to survive by outrunning defenses or overwhelming them with numbers. The B-2, by contrast, is judged by stealth, survivability, and effectiveness in contested airspace. Its speed is secondary. Its size is modest compared to its payload capacity. Its advantage is in the unseen, in the moments when enemy radar returns nothing and defenses are left guessing. Flying the B-2 is unlike piloting any other aircraft. Pilots are not just operators. They are decision-makers atop a network of sensors and systems that provide situational awareness far beyond the cockpit. The aircraft itself fuses information from onboard sensors and satellite data, presenting a coherent operational picture that reduces cognitive load and allows pilots to focus on mission execution and strategic judgment rather than constant monitoring. This integration is subtle but crucial. Modern air defenses are layered and redundant. Radar systems, early warning networks, and interceptor missiles are all coordinated. A single pilot cannot hope to process all the information in real time without assistance. The B-2 does not simply deliver bombs. It orchestrates an invisible advance into enemy territory, deciding when to reveal itself, when to strike, and when to retreat, all while remaining undetected. The B-2's role in modern warfare is not limited to physical destruction. Its mere presence reshapes the battlefield. When adversaries know that a stealth bomber is operational, they must dedicate resources to monitoring and defending against a threat that may never materialize. This is the essence of deterrence. the ability to influence behavior without firing a shot. In an age dominated by sensors and networks, the B-2's invisibility is a force multiplier. The bomber's development was not without challenges. Early concepts flirted with radical designs and unproven technologies. Engineers struggled with aerodynamics, weight distribution, stealth coatings, and engine integration. Maintaining invisibility over long distances required rigorous operational discipline. Even small errors in flight path, speed, or heading could compromise stealth. Yet these obstacles were overcome, and the result is an aircraft that is both technologically extraordinary and operationally transformative. Stealth alone, however, is only part of the story. The B-2 was designed to carry nuclear and conventional payloads, making it a versatile strategic tool. Its internal bays allow for precise targeting while keeping the aircraft nearly invisible to radar. The integration of advanced avionics ensures that navigation, targeting, and communication systems operate seamlessly, supporting missions that require both discretion and lethality. Unlike its predecessors, which relied on large formations to overwhelm air defenses, the B-2 can complete missions solo or in small groups, relying on stealth rather than numbers. This reduces exposure, increases flexibility, and ensures that strategic objectives can be achieved even under the most challenging conditions. It also reflects a broader philosophical shift in air power. Effectiveness is no longer measured by raw firepower alone, but by the ability to shape the battle before engaging. The B-2 spirit is also a statement of technological ambition. It embodies decades of research in materials science, aerodynamics, propulsion, and systems integration. Its design forced engineers to rethink what a bomber could be, to challenge assumptions about weight, shape, and function. In many ways, the B-2 represents a quantum leap in the understanding of air combat, demonstrating that the future belongs to those who innovate invisibly rather than those who compete visibly. Finally, the B-2 teaches a crucial lesson about modern warfare. Success is not always loud, fast, or obvious. The aircraft that survives and succeeds in a sensor-dominated world is the one that moves silently, sees first, and strikes decisively. Its legacy is not just measured in payloads dropped or missions completed, but in the way it reshaped the very concept of strategic bombing. Stealth replaced speed, information replaced brute force, invisibility replaced exposure. The B-2 spirit, in all its silent elegance, embodies this philosophy. It is a weapon of the unseen, a reminder that in modern air warfare, survival, effectiveness, and strategic influence come not from being the fastest, but from being the hardest to detect, the most calculated, and the most disciplined in execution. The B-2 spirit was conceived not as a conventional bomber, but as a machine built to survive the most hostile airspace on Earth. Its primary mission was nuclear deterrence, a task that demanded more than payload capacity or range. It required absolute confidence in survivability. During the Cold War, strategic bombing faced a fundamental engineering dilemma. Radar coverage expanded across continents. Surface-to-air missiles gained speed, altitude, and intelligence. Command and control systems linked sensors into unified networks capable of detecting aircraft hundreds of kilometers away. A bomber that relied on speed alone would be detected long before it reached its target. The B-2 was engineered around a different solution: minimize detectability across multiple domains simultaneously: radar, infrared, acoustic, and visual. This demanded a fusion of aerodynamics, materials science, propulsion engineering, and digital mission systems into a single integrated design. Unlike earlier bombers that were adaptations of existing aerodynamic concepts, the B-2 was built from mathematical radar models first and aircraft shape second. Engineers began by simulating how electromagnetic waves would scatter from various geometries. From those simulations emerged the flying wing configuration: an airframe with no vertical stabilizers, no cylindrical fuselage, and no exposed engine nacelles. This geometry reduced radar cross-section by eliminating right angles and discontinuities that act as reflectors. Instead of returning radar energy back to the emitter, the aircraft's shape redirects it away into empty space. But shape alone was insufficient. The B-2 required materials that could absorb electromagnetic energy rather than reflect it. Radar-absorbing materials were embedded into the composite structure of the aircraft itself, forming layers that attenuate incoming radar waves before they can bounce back. This meant the bomber's skin became part of the sensor battle. The aircraft was not simply painted with stealth coating, it was structurally engineered to behave as a radar sink. For nuclear deterrence, reliability was as important as invisibility. The B-2's navigation and mission systems had to function independently of external signals if necessary. In a nuclear conflict scenario, GPS satellites could be jammed or destroyed. Communications could be degraded. The aircraft needed inertial navigation systems capable of maintaining precision over intercontinental distances without relying on outside references. The engineering challenge was unprecedented. A bomber that could cross the globe, remain undetected, navigate precisely, and deliver weapons with meter-level accuracy. Stealth is often misunderstood as a single technology. In reality, it is a collection of interacting engineering disciplines. Radar cross-section, RCS. Radar detection depends on how much electromagnetic energy returns to the transmitter. Engineers measure this as radar cross-section, or RCS. A conventional bomber presents many reflective surfaces: engine intakes, vertical tails, weapon pylons, and fuselage joints. The B-2 eliminates these features. Its leading and trailing edges are aligned along specific angles that scatter radar energy laterally. The engines are buried deep within the wing, preventing radar from illuminating compressor blades, one of the most reflective components of any jet engine. Access panels and seams are sawtooth shaped to prevent straight-line reflections. Even the cockpit canopy uses conductive coatings to prevent radar from bouncing off the pilot's helmet and internal structures. Infrared signature. Radar is only one threat. Infrared sensors detect heat emitted by engines and skin friction. The B-2's engines are mounted above the wing, shielded from ground-based sensors. Exhaust is mixed with cooler air before leaving the aircraft, reducing thermal contrast. The exhaust is spread across wide troughs rather than narrow nozzles, lowering temperature concentration. Materials in the exhaust path are chosen to withstand high temperatures while minimizing infrared emission. Fuel management systems also distribute heat loads across the airframe to prevent hotspots. Acoustic and visual signature. At high altitude, the B-2 is nearly silent to the ground. Its engines operate in optimized regimes for cruise efficiency and reduced noise. Visually, the dark matte coatings and smooth silhouette make it difficult to detect against the night sky. Stealth is therefore not invisibility, it is engineering probability. Every domain reduces detection chances, forcing enemy systems to work harder and longer to build a track. The B-2's avionics system was revolutionary for its time. Instead of independent subsystems, it used a distributed digital architecture that integrated navigation, sensors, communications, and weapons control into a unified system. At the core of the aircraft are mission computers that process radar data, navigation inputs, threat libraries, weapon guidance, flight control commands. These systems continuously evaluate threat probability and adjust flight profiles accordingly. The aircraft is constantly calculating optimal routes that minimize radar exposure while preserving fuel and timing constraints. The cockpit is designed to reduce pilot workload. 2 pilots manage an aircraft that would otherwise require a much larger crew. Automation handles sensor fusion, threat evaluation, and system monitoring. Unlike older bombers with dozens of analog gauges, the B-2 presents information as an integrated tactical picture. This allows pilots to make strategic decisions rather than micromanage equipment. Redundancy is critical. Every major avionics pathway has backups. Power systems, processors, and data buses are duplicated to ensure survivability in combat and reliability over long missions. The flying wing design that gives the B-2 Spirit its legendary stealth also creates one of the greatest engineering challenges in aviation history. Without a vertical tail or a conventional fuselage, the aircraft cannot rely on natural aerodynamic stability. In traditional aircraft, the tail and body help correct unwanted motion automatically through the airflow. The B-2 has none of those stabilizing features. By design, it is aerodynamically unstable. To survive this instability, the aircraft depends entirely on a quadruple redundant digital fly-by-wire system. 4 independent computer systems continuously calculate the aircraft's position, speed, attitude, and airflow conditions. These computers make thousands of control corrections every second, so fast and so precisely that the pilots never feel the instability beneath them. The aircraft is not being flown in the classical sense. It is being managed by algorithms that maintain balance moment by moment. Every control surface on the wing, 11s, split flaps, and drag rudders, is coordinated through software rather than mechanical linkages. The aircraft constantly monitors its own motion, detects the slightest deviation, and corrects it before it becomes noticeable. This is not simply flight control. It is artificial stability, a manned aircraft that cannot exist without continuous computational support. The wing structure itself is optimized for long-range cruise efficiency. The B-2 operates primarily at high subsonic speeds, where fuel consumption is minimized and thermal stress on materials is reduced. This allows it to fly intercontinental missions without relying on speed for survival. Instead, endurance and invisibility define its performance envelope. Inside the wing is an entire aircraft hidden within a single continuous shape. Fuel tanks are distributed throughout the structure to maintain balance. Weapon bays are embedded deep within the wing to preserve stealth. Avionics systems, landing gear, and environmental control systems are all integrated into the same internal volume. There is no central fuselage carrying the load. Instead, stress is distributed across composite spars and ribs that form a unified structural shell. This demanded unprecedented structural engineering. Engineers had to design a wing that could carry enormous weight, survive turbulence and combat maneuvers, and still maintain exact geometric alignment. Even maintenance access panels had to be engineered so that they did not disturb the aircraft's radar-defeating shape. The result is a flying structure where aerodynamics, materials, and software exist as a single inseparable system. To remain invisible, the B-2 carries all of its weapons internally. External pylons or exposed bombs would destroy its radar signature. Inside the aircraft are 2 bomb bays capable of carrying both nuclear and conventional munitions. But the engineering challenge goes far beyond simply storing weapons. Weapons integration is a digital problem as much as a mechanical one. Each weapon must be fully integrated into the mission computer system. Release timing, trajectory, and targeting calculations must account for aircraft speed, altitude, stealth profile, and the surrounding threat environment. A bomb dropped from a stealth bomber is not just released, it is mathematically choreographed. The aircraft can deploy gravity bombs, precision-guided munitions, nuclear weapons, and hardened penetrator weapons designed to destroy underground facilities. But even the act of opening the bomb bay doors is a stealth operation. The doors are designed to open and close within seconds, minimizing the time the aircraft's interior is exposed to radar. Their movement is carefully synchronized so that disruption of the stealth profile is as brief as possible. Inside the bomb bays themselves, radar reflections are still controlled. The interior surfaces are lined with radar-absorbing structures, ensuring that even internal cavities do not become sources of detection. This means that weapon deployment itself becomes an engineering problem of stealth timing. The bomber must strike while remaining invisible, not only before and after release, but during the act of releasing its weapons. Unlike traditional aircraft that rely on brute force jamming to overwhelm enemy radars, the B-2 relies on situational electronic awareness. Its electronic support measures constantly listen for radar emissions in the environment. These signals are analyzed and classified in real time using threat libraries stored in onboard computers. Each radar system has a unique waveform and frequency signature. The aircraft can identify what type of radar is searching for it and determine whether it belongs to early warning systems, tracking radars, or missile guidance systems. Once classified, the mission computer can choose the most effective response. That response might involve adjusting the flight route to avoid detection zones, reducing emissions from onboard systems, activating subtle electronic countermeasures, or even aborting the mission entirely. Unlike escort jamming aircraft that broadcast powerful signals, the B-2 avoids revealing its presence. Its electronic warfare systems are designed to complement stealth, not replace it. Defensive systems include radar warning receivers, missile approach warning sensors, and countermeasure dispensers. All of these are fully integrated into the same mission computer network that manages flight and weapons. The aircraft does not treat defense as a separate function. It treats survival as a continuous calculation, running alongside navigation and targeting. Stealth is not permanent, it is fragile and requires constant care. The B-2 demands meticulous maintenance to preserve its low observable characteristics. Radar-absorbing coatings must be inspected and repaired regularly. Temperature, humidity, and physical handling can all affect performance. For this reason, maintenance hangars are climate-controlled to preserve the material properties of the aircraft's surface. Every panel alignment is measured with extreme precision. Even deviations measured in millimeters can alter the aircraft's radar signature. This transforms maintenance into a scientific process rather than a routine mechanical task. The B-2 is as much a maintenance system as it is a combat system. Digital diagnostics continuously monitor structural fatigue, engine health, flight control systems, and avionics performance. This data feeds directly into sustainment planning, allowing engineers to predict failures before they occur. Readiness is not achieved through brute inspection alone, but through constant data analysis and engineering discipline over long deployments. The lessons of the B-2 are now being carried forward into the B-21 Raider. Future bombers will integrate artificial intelligence-assisted mission planning, autonomous navigation, advanced materials, and network sensor fusion. Stealth will no longer be limited to shape alone. It will expand into spectrum dominance, control over radar, infrared, cyber, and electromagnetic domains. The aircraft will not simply hide from sensors, it will manage the entire battle space of detection and deception. The goal remains unchanged. Enter denied airspace, survive, deliver strategic effect. The B-2 Spirit is not simply a bomber. It is an engineered system of systems. Its true weapon is not its payload, but its ability to move through the world without being seen. Every line of its design reflects this principle. Geometry, software, propulsion, materials, and human-machine integration. Where once bombers relied on speed, altitude, and mass, the B-2 relies on physics, computation, and discipline. It represents the moment when strategic bombing stopped being about power alone and became about engineering and visibility. Stealth replaced speed, systems replaced brute force, engineering replaced exposure, and the sky was never the same again.